if you have a function which can be written in the form integral of f dash x over fx, and we can even put a k here, with respect to dx, then you can make use of something called the reverse chain rule. In a scenario like this, you would try ln fx, and then you would adjust. The same goes if you have another function which looks like this: k f dash x times by fx to the power of n dx. You would try fx to the power of n plus 1, and then you would adjust. I know right now that makes no sense, but can you just take that down? And then I'm going to go through an example, and then it would make more sense. So let me do A, and then I want you to try B. In this case, the differential is our numerator, the regular function is the denominator. So you're going to try ln and then your function, like this. So by try, I mean you're going to let y equal this, and then you're going to try and differentiate it. So what do you get when you differentiate ln x squared plus 1? You get 2x over x squared plus 1. Okay, that's using the chain rule. Now, you're going to compare this with this. In this case, there is no difference, which means your integral will simply be ln x squared plus 1. If, theoretically, you had 4x over x squared plus 1. In this case, your 4x isn't what you were expecting. You were expecting 2x, meaning you have to adjust what you tried here. You want, or would want, half the amount. That would be your adjustment. By adding a half there, you would end up with this. Okay? Let me go through one. Let me go through B. I think I said I asked you to, let me go through B. And then hopefully that makes a bit more sense. So, again, your function is at the bottom, your differential is at the top. So you're going to let y equal your function, but ln your function, like this. And now you're going to differentiate. What do you get when you differentiate ln 3 plus 2 sine x? You get 2 cos x over 3 plus 2 sine x. Okay? Now, comparing this and this, what's different? It's that 2. You have essentially 2 times cos x over 3 plus 2 sine x. You don't want that though. So you need to make an adjustment. Your adjustment would be to halve your initial attempt. half what you tried to do. Like this. And then plus c and plus c there. Okay? I hope that made more sense. So your function is the denominator, your differential is the numerator. You let y equal ln of your function, and then you differentiate. Then you adjust. You want the numerator, or you want your function, your differential, to look exactly the same as the question. That is the case when you have a fraction, when you have f dash x over fx. The other one was when it's all on the same line, in which case there's no need for ln. You would just take your function and you would add 1 to the power. That being said, question A. Cos x would be our f dash x. Sin x would be our fx. So we're going to let y equal sine cubed. And now differentiate. What do you get when you differentiate sine cubed? You get 3 cos x sine squared x, which is exactly what you have in the question. There is no need to adjust. There's no need to change anything about this, because when we differentiate, we get whatever is in here. So your answer is sine cubed x plus c. Okay, part B. If you get it, do you want to give that one a go? Either way, I'm going to go through it. So, this is our differential. This is our standard function. So we're going to let y equal x squared plus 5 all to the power of 4. And then differentiate it. After differentiating, you should get 8x x squared plus 5 all to the power of 3. Is that what you have here? No. There's an 8 there, but there's only an x there. What can you do to adjust? You can take your attempt in y, but times it by 1 over 8. By differentiating this, you would get that. Okay, I hope that makes more sense now. Can you try this question for me, please? So, in this case, we have cos x squared over 2 plus cot cubed. Let's rewrite this. Let's write it as 2 plus cot x all to the power of minus 3. Then we can put it in that second format where everything was on one line. We let y equal the second part, so 2 plus cot x, and then we add 1 to the power. Like this. Differentiating that would give minus 2 plus cot x to the power of minus 3, multiplied by minus cos x squared. So minus 2 cos x, 2 cos x squared 2 plus cot x to the power of minus 3. So this can be written as 2 cos x squared over 2 plus cot x. This gives us 2 cos x squared bracket 2 plus cot x to the power of minus 3. And then if we write that as a fraction, you get that. Okay. Is that what we have in the question? No. There's a 2 here, and there's no 2 there. What do you therefore need to do to this in order to get that instead of this? What's the adjustment? A half. So your integral would be a half of 2 plus cot x to the power of minus 2. When you have a scenario where your denominator has a power like that, you have brackets and a power, particularly when you have trig, it's better to go with this format than doing the Lun stuff. The Lun stuff will just make your life more difficult. Okay, can you try this question for me, please? So for the first one, you have the fraction format, right? So you're going to let y equal ln e to the power of 2x plus 1. Differentiating that would give 2e to the 2x over e to the 2x plus 1. Like that. Is that what you had originally? No. There's a 2 here that you didn't expect. In order to get rid of that 2, we would want to multiply this whole thing by a half, which means the adjustment would be a half of your ln plus c. Cool. H. I'll do it here. For h, we don't have the fraction format, we have the line format. So you're going to let y equal 1 plus sine 2x all to the power of n plus 1, 5. dy by dx would give 10 cos 2x 1 plus sine 2x to the power of 4. That's making use of the chain rule. Is that what you had originally? No, there's a 10 here. So what do you need to divide by? 10. What is that the same as? Multiplying by 1 over 10. So your integral would be 1 over 10, 1 plus sine 2x to the power of 5 plus c. There you go. Differentiating that would give the question. Cool. There you go. That is the reverse chain rule.